Hey, so welcome everybody to the second DAWS workshop that we are organizing as part of the uncertainty quantification package under DAWS. This one is on uncertainty propagation. The previous one was on validation, and you can find recordings and slides if you're interested in the topic online. So, as John said, today I'm going to open up the workshop with a talk on safety factors against honest QQ. So as we all know, this is an important topic, and this is what I'm intending to cover today. Just a little bit on the safety of engineered systems, what safety factors allow us to do, how are they limited, just a bit of an introduction, perhaps not an introduction, but an overview of how uncertainty quantification comes into play when we talk about safety factors, and what can you do to move forward in an engineering sense. Okay, so really the idea of these workshops is to start breaking away from the academic setting and start moving towards the industrial application. I'm sure you're well aware of the fact that however complex our systems are that we engineer, they mostly rely on deterministic simulations. And we can have very complex, very large models that, unlike experimental testing, give us full field solutions of the quantity we're interested in, but nonetheless, they're deterministic. What this is meant to say is that we usually run a single boundary condition, a single initial condition, a single loading, and so on and so forth. These complex models can be so large that sometimes they're hard to even be run. I was at SciTech in January, where we met with the Society for Combustion Engineering, I think it was, and they're developing models for ramjets, I think. On one occasion, the presenter said, we can't use UQ because our model takes 5 million CPU minutes to work for a single run. So these models tend to be very complex. And unfortunately, their complexity tends to spur confidence in their users, in their developers. So usually you would have one single point answer to within 16 decimal places of what you want to say, and then you say, well, that's perfect precision, so that's it, job done. Unfortunately, all systems that we engineer and subsequently use are surrounded by uncertainty. This could be natural variability and also lack of knowledge about various things in the system, including the design stages. This split that I'm presenting on this slide is going to be very important through the talk, and we're going to encourage today's discussions to be mindful of such splits. So where can the uncertainty in design of aircraft specifically come from and manifest itself in? At the first stage, it can come straight from the requirements phase. Okay, sometimes due to not very well-known mission profile or the tasks in front of the new aircraft, the clients might not be able to specify the requirements very well. So we get uncertainty right off the bat. It can be a technological uncertainty, which is due to the fact that over the lifetime of the design, there may be new technology that becomes available, or maybe we rely on technology that may not become available to produce our design. It can be a process uncertainty. I'm showing obviously a manufacturing plant here, but the process is meant to represent analysis as well. So simulation, calculations, all throughout the design, including manufacturing. It comes in the forms of material variability as well. So we have to select all sorts of materials, especially in aircraft design, to suit the different purposes of the task. And finally, it comes in terms of the loading conditions or the operating conditions that we are going to experience for our aircraft. So as you can see, a very large spectrum of uncertainty, very varied in type and manifestation, and sometimes that puts off people from really thinking about it. So what is actually being done to combat all this in engineering design? So let's take an example design. We have a function, a performance metric that improves with reducing dimensions. Might be weight, might be block fuel, might be anything. But we also have a constraint, which is overlaid here for convenience on that graph. So perhaps we have a stress constraint for this component. And so at some point, we have a critical level of the strength of our component, and that imposes some sort of a limit on our dimensions. So the optimal performance very often is to push your design to the limits of the phase space, right at the corners. That's what mathematics and optimization tell us. But then even though this strategy sometimes guarantees or gives us superior performance, we can run into problems. Chiefly because, for example, some of the factors that are not in the actual design but in the constraints can be uncertain. So here, for example, our force is uncertain, which means our stress is going to be uncertain. And so if we have that, this is actually our safe level right here, and not right here where we already are. So instead of getting a very good optimal design, what we get is a failure of the component. We're exceeding by quite a. So what is the engineer to do in this case? What we can do is we can move a little too fast. We can impose and move our design point away from the limit, such that it's always staying on the safe side of the spectrum. And what this gives us is a safety factor. Okay, and not only can we put a safety factor into the design, but we can also have a safety margin. Now, for those of you, maybe very few in the room, that don't know what the difference is, the safety factor is a multiplicative factor that takes us away from failure, whereas safety margin is an additive distance to the actual failure. How much reserve do we have until failure on top of the safety factor? This is all good. We're quite away from the failure point now, but we end up in suboptimal performance. So some basics on safety factors, they tend to be fixed values. Okay, so part 25 here is CS 25 postulates that we should use safety factors 1.5 in aircraft design unless anything else is specified. Of course, there are exceptions. For example, pressurized cabins are 2 and landing gear is 1.25 or something like this. But in general, aircraft engineering is known for the safety factor 1.5. And so, why 1.5? I mean, this seems very, very close. When I was preparing for this talk, I had to revisit my whole lectures. I was amazed by the actual history of the safety factor. So, in the 1920s, aircraft were designed for 3 conditions. The safety of aircraft was defined by 3 conditions. So, dive recovery initiation, you start to pull up. Recovery from a pull-up, so you've pulled up in one level of an inverted flight, believe it or not. And so this was found, the 1.5 safety factor was found to be giving a good compromise between weight and safety. But what do we mean by good compromise? There was no statistical justification. Instead, planes were designed with different safety factors, and the one that had 1.5 safety factor were observed to be flying safely. So that was the reason, at least in the early 20th century. So as new data began to roll in from more aircraft designed with the 1.5 safety factor, that became the rule. And you can immediately spot the problem here. If planes designed with a safety factor 1.5 were observed to fly safely, you would naturally want to produce more of these. So that would bias your learning about what a good safety factor actually is. So this rule is actually quite biased. Okay, so what does the safety factor cover? So what we intended to cover is loads that exceed momentarily, hopefully, our design loads over the limit of which set, some structural deflections above the maximum deflection we're designing into the system, and manufacturing tolerances not including the stress analysis. What I mean by this is, that's very interesting. What I mean by this is, we have a manufacturing tolerance. So the part was produced within that tolerance, but maybe the tolerance itself didn't feature in the analysis. And so this is not a blatant error. Okay, that's very important, because we also have things that the safety factor does not cover. Okay, does not cover bad engineering, bad design, natural material property variation. So you have to select your so you have to select your material, and it doesn't cover poor craftsmanship. What are the implications of having all these covers and non-covers? So because it doesn't cover many things that naturally occur during the design process, we don't actually get a guarantee that the design will not fail. We are further away from failure, but because it's just a multiplicative, deterministic, and scalar factor, we don't have, that it doesn't come with any guarantees. And this is true for any value of a safety factor. We can put a safety factor of 3. We can beef up the wings. We can make massive spars out of steel. There's still no guarantee that the people will fail. It results in using expensive materials. So because it doesn't cover material variation, we have to be very picky in selecting the material. It has to be very good quality, very tightly monitored. And the same thing goes for production lines. So we have to have very strict protocol about manufacturing, what is coming on the conveyor lines and what is coming out of them, really, how things are being assembled, and so on. We also have strict maintenance. So the fact that aircraft are designed with 1.5 safety factor makes, yes, it makes them safe, but it also makes them susceptible to very regular maintenance. So you have to really go and inspect them very regularly, on very tight schedules. And it also puts a very tight schedule on the end of life. Finally, there's a very strict operation protocol. So that means that, I mean, I'm sure you've all seen, like, you can't board, you can't take that much luggage in your aircraft. It has to stay behind. That's because it violates the operation protocol, or the wind is above certain speed, you can't take off, and so on and so forth. And so all this results really ultimately in a very much increased cost of development and operation. And we said that the safety factor is based on observed planes that flew well or safely, but what if there is no prior knowledge? What happens then? And I mean, this is always amazing. For all the technological advancements, let's take a look at the out of mold line of aircraft over the last 70 years. So we started with DC-3, the Dakota, in 35, moving to Boeing 377. A few years later, first kind of successful passenger airliner. Then we go on to the DC-8, and you can immediately start to notice a pattern, right? Then we go to the 340, and finally we move to the 380. And what is the pattern here? We always stick to the same tubular fuselage with long slender wings. Okay, that is not to say that it's a wrong way to design aircraft, but it's the same outer mold line. So people tend to rely on their previous designs to learn and to make incremental progressions in their new designs. And so over 70 years, we see very little in the sense of radical changes, even though they might be designed. So there's what do we do about this 1.5? Can we reduce it? There is what's called a waiver for safety factor. It's a decision to lower it, actually. So if you want to optimize weight and whatever, you can lower your safety factor. And a NASA study from about 10 years ago found out, it was against the waiver, but it found out that waivers are most usually justified as the load being well known. Can you imagine that? I mean, somebody wants to lower the already low 1.5 safety factor to whatever, because they know the loads very well. This is interesting. And I hope to be able to discuss this justification today. Yes,
good question.
Of course.
Does this apply to the safety factors? Does it apply to every structural component?
Yeah, the waiver?
No. More generally, the 1.5. Is it every structural?
No. It's a general overall aircraft safety factor, but you can have. I mentioned in the beginning, for example, I think, Simon, correct me if I'm wrong, Pressurized cabins are 2, safety factor of 2. Landing gear is 1.25. Some pressure lines are safety factor of 3 or something like this. So it varies from component to component.
Flutter is 1.15.
Yeah. Flutter is 1.8, exactly. There you go.
Safety cases of systems failures, of probability of failure. So, you reduce safety factor due to probability of system failure. So there's a curve of
Spoilers.
Probability of failure.
Spoilers.
I'm sorry, Peter. Sorry, Peter.
So yeah, it's it can vary from component to component, but that doesn't mean that you have actually taken into account what this component experiences in terms of uncertainty for its environmental conditions, for example. Okay, so yes, so the main justification was that the loads were well known. And what that same report also found is that engineering judgment was utilized to make a decision whether or not to go and lower the factor. Another finding is that we can have a no-test safety factor, which to me is quite scary, right? So they found this really applies to spacecraft, but I decided to put it anyway because it just to me it's mind-boggling. So they found more than a dozen cases where people decided to do not test their structure, put a safety factor anywhere between 2 and 2.6, and go.
They're saying the sound isn't very good.
The sound isn't very good.
Can you speak about facing?
Yeah. Can you hear any better now?
Yes, Jack speaking from Toulouse. Yes, it's much better now.
Okay. Could you hear the questions? Or not really?
Not really the questions, but everything else is okay.
Okay, I'll try to repeat the questions. Thank you. Yeah, okay. And so we're actually already discussing this. How is this, what does this tell us about the qualification by analysis, certification by analysis strive that we are experiencing in the recent years? I mean, does that mean that ultimately we can go and just have a numerical design, don't test it, and try to certify it by just applying a large safety factor? Unlikely, but it's something that I would like to question myself about. Final point about safety factors is that the fact that it's been set as 1.5, it doesn't mean that you can just leave it there. It must be monitored throughout the life of the system because it degrades due to material degradation and normal wear and tear. So that kind of justifies the cost of maintenance, the high cost of maintenance. Okay, so a few main points just to finish up with safety factors here that really are going to be useful for the following discussion. Safety factors are fixed post-hard values or post-analysis values. They come after you compute all your stresses and strains and displacements. And Gareth, perhaps that kind of great comment here answers the question. It varies across components. The uncertainty that different factors carry with themselves doesn't really affect the safety margin because of the first point. So we may know that one factor is more uncertain than the other, but that doesn't matter because we're just put a safety factor after the analysis system too. So yes, some factors are well known, so they're justifying a potential waiver, but others are not so well known. So we can't treat them all the same. One very important drawback of safety factors: it doesn't distinguish controllable from uncontrollable uncertainty. And so what that is meant to say is that even if you knew you could improve your design in a certain way or reduce the uncertainty in a certain way, you couldn't do it through the safety factor, only because it comes after the analysis. Safety factors do sacrifice optimality, but they do so without really providing a guarantee of safety. It does take you further away from failure, but it doesn't give you any guarantees. And of course, new materials, architectures, and potentially even technologies can challenge the use of safety factor and can even potentially cast it to be viewed as a roadblock to implementing new technologies. So what is an alternative then? We have our example from before. How about we trying to identify the uncertainties that might plague our design, try to characterize them carefully, and then propagate them through the design from start to finish. So the uncertainties can be in the loads of our system, right here in the force, and uncertainty in the force, as we saw in those margins before, would propagate to uncertainty in the stress, or they could be in the actual design factors themselves. The good thing about doing probabilistic analysis is that you can actually do arithmetic with these things. They're mathematical entities, so we can do arithmetic with them, and you can, as an effect, calculate the probability of failure. Okay. So this expressed uncertainty, whether it's accurate or not, is now an entity that you can work with, and it can be reduced to determine a new safety margin, which is quantifiable. Okay, so you no longer do this post-analysis; you do it during the actual analysis. What this gives you is some defensible reliability arguments. So again, this is probability, so there is a chance that the design still fails, but at least you can defend why you've taken a decision. Probabilistic risk can be used in trade-off studies. So you can trade risk for performance. You can decide that a component is very critical, so you don't want to risk it too much. You risk performance. And also, as a byproduct of performing risk analysis, probabilistic risk analysis, is you get a larger picture of uncertainty. So in order for you to do probabilistic risk analysis, you have to have identify, characterize, and propagate your uncertainty, which then can be used in other domains in the design. So you don't end up just with risk analysis. What it really ends up with is an optimized, uncertainty-aware design. Now, when I say optimized here, this is a disclaimer. Today, I don't want to be a blind advocate of just go and do risk analysis. That's the end of the world. But to discuss what optimized means, what uncertainty-aware design means as well, in that sense. Okay, you say you propose this new strategy, but uncertainties in the design are too many to identify, okay, or too many to identify reliably. They're too difficult to quantify. So what do we do if we don't know how to quantify them? How do we express uncertainty? There may be complex relationships. So do we assume everything is independent? Do we factor in for some dependence? There are some very well-known dependencies based on engineering judgment that might be difficult to capture. And what if once I propagate the result, once I propagate the uncertainty, it's so large that it invalidates my result. It floods whatever precision I have. And if this happens after I've used all my compute resources, then what is my design good for? Okay, and I could say that it's always been cheap to fail. So it's always been cheap to get a wrong answer. And so safety factors really come as almost as a curtain in front of you, and they present almost an engineering solution to the whole uncertainty quantification problem. So we, like engineers, like to be pragmatic about things. And so why bog down in all this when you just have a safety factor? Okay, so with this, let's examine some of the, to be honest to ourselves, let's examine some of the drawbacks of probabilistic reliability assessments as well. So they will only be as good as our uncertainty quantification has been. Okay, identification, characterization, propagation. So that needs to be done carefully. You cannot be fudged. But then, how do we construct those distributions that we saw in the previous slide? Do we use very well-known methods, maximum likelihood or maximum entropy, or the very well-known and popular Bayesian treatment? Do we consult experts to give us those distributions? And there's plenty to not know about the distributions, right? We can ask questions about the shape or about the parameters of the distribution once we select the shape. And really, safety assessment is about the tails of this distribution, so very rare events. If we get the central tendencies very right, very correct, but we miss the tails, then our risk assessment really goes down the drain. So really, we should ask, how confident are we in the estimations of the distribution we have? Is all the uncertainty, we think, down to random variations? That is to say, if we assign a distribution, does that describe everything that we don't know about the system? Okay. And the truth is that if we start asking questions about these three topics, very quickly you will realize that we can't assign precise distribution just because we don't know what to assign. It's not because it varies. Okay? So then we can say, okay, we only have 3 data points or 5 data points. So how do we construct a distribution, even an empirical one, from so few data? And can we also take measurement uncertainty into account when we try to develop a safety approach towards design? So with this, take a look at a brief breakdown of the field of uncertainty quantification. So we have uncertainty, as we said so far. That splits into variability and ignorance. These are the 2 main types that we observe. I'm sure most of you here are aware. We do also have some other types, like volitional uncertainty, which is due to us not being able to make up our minds about things. Some vagueness, so poor definitions of the problem, and some conflict when we have different experts. For today, we're going to focus on variability and ignorance. Now, variability is usually, and rightfully so, treated with probability theory. Okay, whereas ignorance is taken care of through imprecise probabilities or interval analysis. So what this allows us to do then, this split, is to conduct reliability assessments only with what we know, not trying to characterize what we don't know, but only with what we know. So for example, if we know something about our factor, which is the minimum max of our factor, our design factor, we can construct an interval. We don't know anymore. Okay? But what if we also add a mean? We can construct this funky shape, which is called a probability box, okay? Which bounds all probability distributions, all cumulative distribution functions to be precise, that have minimum value of 1, maximum of 5, and a mean of 2. Okay? So that's all we are supplying to our uncertainty system. On top of that, if we know something about a standard deviation, like it being 0.5, we can reduce the range of uncertainty further. We can say, oh, also we know, or we expect, or maybe we know, that it's a unimodal distribution, and the mode is at 2, so it's coincident with the mean. And finally, after the course of developing our design and gathering more information, perhaps we end up at the place, well, it's actually a normal distribution. Okay? But importantly, we don't start, we start right here. Okay? So if you were to overlay all these distributions, they would all fit, all these uncertainties, I'd say, they would all fit in the beginning interval. So we didn't inject knowledge, artificial knowledge in our design. Okay, fair enough, but where do we stop with this? I mean, we saw there are 5 branches of uncertainty, there's plethora of mathematical methods. What do we do to keep it practical and keep it engineering? So truth is that non-deterministic analysis can be combined with safety factors. It doesn't preclude us, that all this doesn't preclude us from using safety factors. But the only thing is that now the safety factors will be non-deterministic. So the same way that we can propagate the response, the input uncertainty to the response of the analysis, safety factor being a multiplicative factor, that also means that the safety factor itself will turn into whatever uncertain number we've chosen to express the uncertainty with. Can we repurpose then the safety factor into a tool to deal with the unknown unknowns? As Don Rumsfeld famously once classified the unknowns. Can we then charge the safety factor with the residual uncertainty that is left after the probability distribution system. And finally, can or should really, I ask, UQ and safety factors, uncertainty quantification safety factors, replace decision making? So does it really give us tools to take the decisions out of the hands of humans and put it in the computational routine? Just to conclude, so safety factors are not the end of the road for engineering. Just on the contrary, they're very close to the surface, and we can do reliable, efficient, and novel possible designs with uncertainty quantification, and perhaps with safety factors as well. So with this, I would like to really encourage you for today to think about challenging the assumptions that go into your designs. Can we think about what has grown on us to be just an assumption and what is knowledge? We differentiate with that. Can we try to be honest about our uncertainties? Try to identify all that we think that is we don't know. Today we'll have plenty of presentations on how we actually propagate what we've just specified, or propagate it to the models, and hopefully together doing 3 discussions to find a way forward for uncertainty quantification and propagation in aircraft engineering. So with this, I thank you very much for attending, for being with us here today, and I'm happy to pass on. Thank you.
Okay, thank you, Peter. I think that was a really good presentation, but we've used up all the time. So, were we intending to have questions right at the end, or would you like to take questions?
I suppose a couple of minutes for questions is okay.
Okay, so if anybody's going to put in a question.
Right, yeah. Any questions?
So you showed the 2 forms of uncertainty, and I'm glad you restricted it to those. And you seem to dwell on the probabilistic, what I would call the aleatoric uncertainty, rather than the epistemic, where you have ignorance. Is that going to feature much, and does it feature much in the work you're doing?
Which is the feature, sorry?
The epistemic, the one that's based on ignorance.
On the contrary, actually, we are very, very keen on distinguishing the two and treating ignorance or epistemic uncertainty in its own right way with interpoint analysis and so on. So not mingle the two. I don't, maybe perhaps it came across this way, that you say that we're mixing them, but no, we're trying to be very careful with distinguish the two.
Thank you. And in fact, I would say epistemic uncertainty is the driving one in most of the applications we have in Airbus, certainly, yes.
Oh, really? Yeah, sorry.
It's the one you can do the
I'll
most
just repeat the
about.
questions, I think. So, as a matter of fact, all these uncertain numbers are all aware of epistemic uncertainty. That's why they don't look like normal distributions. These probability boxes. So the width here between the 2 bounds is representative of epistemic uncertainty. This is the case where you don't have any epistemic, so you have a precise distribution. But in all these, you specify partial information. So you can only with surety, you can only say this is what my uncertainty looks like until you break down and say, well, it's a normal, and construct this precise probability distribution. Does that answer your question? Yeah.
Yes, thank you, Peter. So